Okay, so we're looking at polynomial functions, the characteristics of them. So polynomial function is in simplified form in this form. Okay, that looks kind of complicated, but take a close look. It's just got an x to the n, so whatever, say if it's a degree 4, that would be x to the 4, x to the 3, x squared, x and constant. And n is just the coefficient of that particular term, right? So a's are just the coefficients of each term. So the a's are real numbers. So the highest power of the variable x is called the degree of the polynomial function. So you learned that in Math 10. The coefficient of the term of highest degree is called the leading coefficient. Because we like to show our polynomial functions in descending order of degree. So the highest degree term will be first, and the a value is the leading coefficient. So the term whose value is not affected by the variable is this term here. There's no variable there. It's the constant term. Okay. So in the general case here, the degree is n. The leading coefficient is a subscript n, and the constant term is a subscript 0. Okay. So you've previously studied degree 1 polynomial functions called linear functions. They are expressed in the form, most commonly, y equals mx plus b, but really that m is the leading coefficient. That's an a, right? You've studied degree 2 polynomial functions, quadratics, in the last 2 units. They can be expressed in the form y equals, so that's really the first unit we did together, ax squared plus bx plus c. So again, this is your leading coefficient, is the coefficient of x squared. And so now we're looking at cubic, quartic, and quintic. We're doing that in this course, so this isn't part of 20-1. This is because you're in IB. So we're looking at it in detail now. Again, in 30-1 IB, we'll do it again. A little bit faster because you've seen this before, but it is going to be, it is part of the 30-1 curriculum. So we're not going to spend as much time next year on it so that we can fit in the few topics that we need to, that are IB topics at the 30 level. So just like you did last semester, you did rational expressions and equations in Math 10C. That's normally 20-1. We did that to free up time this semester. So same thing, we're trying to free up time when we can because we have a big unit at the end of this course on stats and probability. That is IB only, okay? So here's some examples. We want to basically use our inductive reasoning to come up with some properties. So which of the following to the right, functions to the right, well, below actually, which are polynomial functions, and then for those, state the degree, leading coefficient, and constant term. So remember, the exponent on x needs to be a whole number. So 4, 1, 0, that's good. 3, 2, that's 1/2, right? If we convert it to a power, so that's not a polynomial function. 1, 5, the root 3 doesn't matter. That's a real number. That's fine. So that is 2. This would be x to the -1. And -1 is not a whole number, so that's not a polynomial function. And then here, the last one, if we expand that out, we'll get something x cubed. Okay, so we'll get an x cubed. So that is. Okay, so the degree for these polynomial functions, highest degree is 4. Leading coefficient on the x to the 4th term is -2. And the constant term is 1. All right. Then this one here, the degree is 5. The leading coefficient, so this is not in descending order of degree, but we need to take that coefficient of the x to the 5 term. We rearranged it. It would negative root 3 x to the 5th. So this is negative root 3. And then the constant term has no x's in it, so it's 6. Okay, so then that one isn't, then this one, degree 3, because if you expand this out, this will be a quadratic, okay? X squared times x is x cubed, so that's degree 3. Now what will be the leading coefficient? Well, if I expand out, you don't have to expand out the whole thing. If I use FOIL here, I'll get 2x squared plus other terms, and then I multiply by negative 4x. So negative 4x times 2x squared is negative 8x cubed. Everything else, Gus, can you get your pencil out? Can you get your pencil out? Okay, so the leading coefficient is negative 8. And the constant term, now that, again, do we have to do all of it? No, we would care about this. That's negative 15. Multiplied by negative 4x, not going to have a constant term. So this has a constant term, but we're multiplying by x. So there is no constant term. Okay. I guess you could put 0, but we don't even include that. All right, so back to math 10. For the function y equals 2x minus 6, I'm just going to erase this. Y-intercept, so that's in slope-intercept form, right? That's your y-intercept. In factored form, factor out the 2. Okay. Says algebraically determine the x-intercept and use it to sketch the graph. Well, if we didn't do the factored form, our x-intercept is when y is 0. So when we solve that for x, we get x equals 3. Notice how, when it's in factored form, that tells us our x-intercept. So think back to quadratics when it was factored. We looked for those factored forms to get the x-intercepts. Same thing. Now, when you learned equations of lines back in Math 10, you probably did it this way. But now that we've reviewed factoring, done quadratics, you can do it this way. A little bit easier. So, describe the end behavior of so we're going to sketch the graph, sorry. So x-intercept of 3, y-intercept of negative 6. Okay, and then draw a line. Okay. So that's the line that has equation y equals 2x minus 6. Describe the end behavior of the graph. So what does that mean? Well, it means what happens at the ends of the graph. Where are the arrows going? So at the leftmost, this arrow is going down and to the left, and it's going to end up, it's already actually partially in quadrant 3. So when we describe the end behavior, we say down in quadrant 3 and up in quadrant 1. Okay. Sometimes we might even just, this is more descriptive. You might say it has a positive end behavior. So write that in as well. Okay. Because at the end, the far end, the graph is going up, which is the positive direction, up and to the right. Okay, so it's positive end behavior. To be more specific for this particular, what happens is because it's linear, it has to do opposite directions. So it's going down in quadrant 3. Okay, so this is, let me label it in red here. So quadrant 3 is here, quadrant 2 is here, quadrant 1 is here. 3 up in quadrant 1. Okay, so sometimes you're just going to be asked to describe the end behavior. All right, we'll go to the next step. So now we're into a quadratic. So this says, for this function, state the y-intercept. Okay, so y-intercept is -8. That's a review. Factored form, that's a review. Okay, so factor that. Okay, so what is that factor to? X minus 4, x plus 2. Then it says state the vertex. So, it doesn't say use your calculator. So you could go back to the beginning and complete the square, right, and find it in vertex form. But a little bit faster than that, because we have it in factored form, if we were to start sketching this, this would be x value for x-intercept, of -2. Where's the vertex going to be? What x value will the vertex have based on that information that I graphed? Yep.
It'll be 1.
It'll be 1, right? Halfway in between, right? So the axis of symmetry is the average. So x equals -2 plus 4 over 2 is 1. So that's the axis of symmetry. So our vertex is going to have an x value of 1. And then just substitute that back in to get y. 1 squared is 1, minus 2 times 1, minus 8. So what's that? -1 minus 8 is -9. So that actually have to complete the square. We factored it. Okay. So that is going to be, say, down here. 1, -9. So algebraically determine the x-intercepts. Well, we've already done our work here. X-intercept is when y is 0, so we're putting 0 into our factored form. So there's really not a lot of work because we did some of it already. So for the function, we take a look at the leading coefficient, it's positive. So we can say positive end behavior. And then let's be specific, okay? Take a look here. So it's going up and to the right because it's positive end behavior at the far end. At the beginning end, it's going up and to the left. So this is quadrant 2. This is quadrant 1. So we would say up in quadrant 2 and up in quadrant 1. Okay, so it's hands up, right? It's a U shape. It's a parabola. Okay. So we reviewed a linear and a quadratic. They were expressed in simplified form. Their y-intercepts, respectively, are. So we did that. So what was the first? The linear was 6, was it? Or -6? And that was -8. Okay, so -6 and -8. When an equation is expressed in simplified form, the y-intercept is obvious. State the y-intercepts of each of the following higher degrees. So these are degree 5, 4, 3. Just state the y-intercepts. Looking at the constant terms. 6, 1, d. Then factored form is written out again for you there that we did. The x-intercepts of the linear, there's just one of them, was 3. X-intercepts of the quadratic, I'll put them in numerical order, -2 and 4. Okay, so now take a look at these higher degree and state the x-intercepts. All you do is look at the factors and figure out what x value makes each factor equal to 0. Okay, everyone should be doing this. Who's not on your phone? So remember, if there's a coefficient on x, it's the opposite sign of the constant, divide by the coefficient. This, if there's just an x, nothing added or subtracted, it's 0. This, there's nothing that's going to make x squared plus 1 equal to 0. If you try that, you will get x squared equals -1, and there's no way. You can't take the square root of a negative. So that's not going to give you any x-intercepts. This one here will be -7 over 4. So in sort of this general factored form, you take a look opposite sign of the constant, so that'll be b. Here it'll be d over c. This will be -f over e. So obviously at each x-intercept, the corresponding y value is, oh my god. Set here. Corresponding value is 0. So the value of the polynomial function at each x-intercept is 0. That's why if you're dealing with a function, it's called a 0 of the function. Okay? So since the value of the polynomial function is 0 at each x-intercept, the x-intercepts are also called the zeros. We talked about that with quadratics. For a polynomial function p of x, if p of a equals 0, then a is a 0 of the polynomial function. And so those are the coordinates of the x-intercept. Okay, so now we'll examine the effects of the degree and the sign of leading coefficient on a polynomial function. The following equations are represented in simplified and factored form. If the graph isn't provided, sketch a graph, state the intercepts, label them on the graph, domain, range, description of the end behavior. And then if we need to, round values to the nearest 10. Okay, so these are linear. So it's factored, simplified and factored. We already did this one. The y-intercept is -6. The x-intercept is 3. So we already did that one. Remember, the domain of any polynomial function is all real numbers. Okay, and the range of a line is also all real numbers. And then if we describe our end behavior with regards to quadrants, then it's up in quadrant 1 and down in quadrant 3. Just want to check something. So next one's a different one. Simplified form, factored form, y-intercept. Look at the slope y-intercept form, so it's -12. Got that. X-intercept, go back to the factored form, so it's opposite sign of the constant, -4. Okay, so the domain is all real numbers, as is the range. Okay, anytime they're going, I call them distal moves, right? The arrows are going in diagonal quadrants, so that's always going to be a range of all real numbers. So end behavior here, it's up in quadrant 2 and then down in quadrant 4. Okay, so for a line, it's going to be diagonal quadrants. One's up, one's down. Okay, depending on the slope. And the only exception to lines would be a vertical and a horizontal. Okay. All right, degree 2. We already did that one as well. It's simplified form, factored form, y-intercept. Y-intercept, we can just look at the constant term. X-intercepts, we already did that, -2 and 4. Domain, all real numbers. Range, you need to know that vertex. And we did find that. So remember, it's y greater than or equal to -9. And the end behavior is, well, it's up in quadrant 2 and up in quadrant 1. All right, so the next one is a new quadratic. It's factored for you. So I'm going to give you a couple of minutes to do that quadratic, and then you do the cubic. Okay, so quadratic, just check your work here. There's one on the right, factored form, the simplified form. So the y-intercept is -3. X-intercepts are 1/2 and 3. Range is everything less than or equal to 3.1. And so the end behavior, both ends are going down in quadrant 3 and in quadrant 4. Then cubic, y-intercept is -15, x-intercepts of -3, -1, 5/2. Arrows are going in diagonal quadrants, so it's all real numbers for range. And so one's up and one's down. Up in quadrant 1, down in quadrant 3. Okay, or you can say them in the other order. Doesn't matter. Okay, and then another cubic. So y-intercept of -6, x-intercepts of -2, 1/3, and 3. Okay. Arrows going in diagonal quadrants, so all real numbers. Up in quadrant 2, down in quadrant 4. Okay. Then degree 4 and degree 5. So I'll give you a few more minutes to do degree 4 and degree 5 there. So you can take a look at the solutions there, check your work. We're going to summarize what we did in this big chart on the next page, because there's some patterns, right? So if you're taking a look at the degree 5, notice how the range was all real numbers and the end behavior was in diagonal quadrants. So that's degree 5. Degree 3, same thing. That's an odd degree. Then the previous page was degree 1. Same thing. Okay, all real numbers up and down in diagonal quadrants, either 2 and 4 or 1 and 3. So odd degree will always have a domain, a range of all real numbers, one quadrant going up, one quadrant going down, where the quadrants are diagonal. Then if we look at the even degree, the arrows are always either going up or down. Okay, for degree 2, degree 4, same thing. Might zigzag in between, but it's still going both up or both down. So that means the range will be either less than or equal to a number or greater than or equal to a number. Okay, and the end behavior will be both ups or both downs in horizontal quadrants. Okay, so let's just, one more thing I wanted to point out here is when we're looking at the cubic, so this had a positive leading coefficient, so it was going diagonal from quadrant 3 to 1, so up into the positive quadrant 1. Here, negative leading coefficient ends in quadrant 4. Okay, so I always look to the end because a positive leading coefficient always ends in quadrant 1 going up. So positive leading coefficient up and to the right, negative leading coefficient down and to the right there. Whether it's whether it's degree 3, 4, 5, whatever. Okay, so there's a connection and let's look at it. So domain for all of these is all real numbers. So you can just do a little ditto all the way down. So the range, if we have an odd degree, so 1, 3, 5, positive leading coefficient, so that basically means it's going to zigzag somehow, okay? And so the range, those are my disco arms, is going to be all real numbers. Okay. And if it's a positive leading coefficient, it's going to end in quadrant 1, right? If we think about that. So, and then diagonal quadrants, it's going to be down and up, or up and down, whichever you want to put first, but they're going to be opposites. If it's a positive leading coefficient, it's going to be down in quadrant 3 and up in quadrant 1. And here's a space where we can put the, so here, I'll put it in red, ends, and the ends. So odd and negative. So same deal here. If it's odd degree, it's going to be all real numbers for range. But it's going to end in the, I'll do it over here, in the quadrant 4. So the arrow there and the arrow up there. So you can say up in quadrant 2 and down in quadrant 4. One up, one down. Now even with a positive leading coefficient, that's got to end going up here, and it's got to start going up. Okay, a parabola with a positive coefficient would just be a U in between there. Could be a higher even, so it might zigzag. So the range then, we don't know the specifics, right? But it is going to be greater than some number, and what we'll just call that number now is the minimum value. So we'll just say y greater than the minimum, because we don't have any specifics about it. And so both are up in this case. 2 and 1. Okay, and then the opposite is for negative. So that would have your ends both going down. So your range would be y less than or equal to the maximum value. And these are both going to be down. And that's quadrant 3 and quadrant 4. So below are 3 different degree 4 polynomials with their respective equations. State the difference between relative max and mins and absolute max and mins. Use the graphs above to help with your explanation. So here, this one has a absolute, what's called an absolute minimum point. Okay, that point here, there is no other point anywhere that's lower than it. Okay. So absolute anywhere on the graph. Whereas this point here is what we call a relative min. This is a relative max. This would be an absolute min. Okay, because there is nothing anywhere else that's lower than it. But here, that relative min is relative to the points around it. It's the minimum, but there are other points in the graph that are lower. So that word relative means relatives are close to you, right? So there are, if you think about in your family, so relative to the points directly around it, that's a minimum, okay? Relative to the points directly around it, that's a maximum. But relative to the whole graph, it's not, right? Comparing this point to the whole graph, so we can't say it's an absolute maximum. This one, compared to the whole graph, that is the lowest point, okay? I'm recording, it slows everything down. Okay, so then describe the relationship between the degree n of a polynomial function and the shape of the graph with respect to the relative max or mins. So here, take a look. This was degree 4, okay? So we just had 1 min. Here, this is degree 4. We had 1, 2, 3 maxes or mins. Here, this is a weird one. It's degree 5. No, sorry, it's degree 4 as well, sorry. And it has 1 min. So basically, remembering that degree 4, for example, both arms have to go up or both down. We couldn't have this ending back down here, even with a zigzag in there. Okay, so the maximum number of min or max points on your graph will be one less than n. Okay, so and I call them turning points. Okay, so the graph of an n-degree polynomial will have a maximum of n minus 1 turning points. It can't keep zigzagging more if you're going to more than n. Okay, so this middle one is a really good example. That's the maximum. And if you think about it, if it's degree 4, the maximum number of x-intercepts they can have is 4. Can't get more than, if we had another one there, we would have to have another factor with x in it, which would make it degree 5. So the maximum number of x-intercepts is 4. Could be less. That had less. This has only 2. Okay, but the maximum number of x-intercepts is the degree. The maximum number of turning points is 1 less than the degree. Okay. So if we wanted to, we're asked here to sketch a graph, any possible graph, degree 6 with a positive leading coefficient. So I know it's got to be up there and up there. Positive, and it's even degree. Okay, and then I'm just going to zigzag it through to have 6x intercepts. So they're 1, 2, 3, 4, 5, 6. I'm going to skip this one, let's do this one. Degree 7 with a negative leading coefficient. So I know it has to go down and to the right. Odd degree, so it's got to go up and to the left. And then I'm just going to zigzag. 1, 2, 3, 4, 5, 6, 7. Now, that's the maximum number of x-intercepts. 1, 2, 3, 4, 5, 6, 7. This could be all shifted up, right, so that there's only 1. But it has to have an arrow at the top left and the bottom right. All right, so next one, the graph of a polynomial function is shown. State the degree of the function and the sign of its leading coefficient. Okay. So first of all, it's up and to the right, so I know it's positive. Okay. Degree, well, it's got 4 x-intercepts, but it's got some zigzags there, right? So if we were to shift that down, it would have more x-intercepts, okay? So kind of have to think about that. The number of x-intercepts is not necessarily the degree. The degree could be higher. So I think about it as the side. Almost we call it side sometimes. So this is one side, and there's a turning point, right? So there's another side, a turning point, side, turning point, side, turning point, side, turning point. Okay, so if you follow that through, it's 1, 2, 3, 4, 5, 6, 7, 8. How many relative max or mins? 1, 2, 3, 4, 5, 6, 7. One less than the degree. Okay, so you can think about it as the sides of it or the turning points. This one's factored, state the x-intercepts. Careful on this one. It switched around, but it's going to be 4. Algebraically determine the y-intercept. That's when x is 0. Oh. Sign of the leading coefficient. So now be really careful on this one, because when we expand that out, we're going to take the x, the highest degree term in each, and multiply it together. So x times 2x is 2x squared, times x is 2x cubed, times negative x is negative 2x to the 4th. So negative 2 is your leading coefficient. Degree of the polynomial is 4. And sketch without a calculator. So we're going to give you this information maybe without a polynomial function, so that you have to sketch it and you can't just punch it into your calculator right away. You would have to build the equation yourself. So be aware of that. So we've got our x-intercepts. Okay. Y-intercept. So we're doing a sketch. We're not scaling anything out. And so negative leading coefficient has got to be down and to the right at the end, and it's an even degree. So I've got to be down here as well. Okay. These are all single factors, right? So I'm just going to zigzag through them. So maybe not use that particular arrow. That'll go up, down, up, down. That's approximately what it's going to look like. Then you can enter it. I'll let you do that on your own time. Enter into your calculator to verify. And then, yeah, I'm going to leave this because we're getting short of time here. I'm going to let you do this part on your calculator. Okay? You're going to want to find that maximum point, because you're going to have to do the range, right? It does say each max and min, so find all of them just so that you can plot them. You're not really going to do that on a regular basis. You just need it for your range. So let you do that on your own. 12 you can do on your own, and then let's just summarize together here. Okay? So in the box, there's your polynomial function. The domain is always all real numbers. Range is all real numbers if n is odd. Very nice. Okay, it will be y greater than k, where y is the absolute minimum. That will be if n is even, and the leading coefficient. So y is greater than, it means it's opening up. So the leading coefficient has to be greater than 0. And then this would be even, where the leading coefficient is less than 0. Okay, so you can finish those 2 questions, and then there's lots of practice, and there is lots of questions from the textbook. You might not get through it all tonight, but notice tomorrow there's no questions assigned from the textbook tomorrow, so you can always